called SPI. So how it is computed? Again, you have to select a variable and you have to select a duration. Of course, you may say, but the variable is already selected because it's precipitation, correct? But let me say that the standardized precipitation index is what you often get mentioned. But the same index can be used for river flows. And in fact, there is a similar index, which I will just mention, which is computed in the same way by using the variable river flow instead of the variable precipitation. But I wanted to introduce the standardized precipitation index because this is the entry. And if you try to Google it, you will see how many entries you get. Standardized precipitation index. You see there are more than 200,000 entries, and even if I put the commas, you see 5,000. And let me see if I put the Z here, what happens. 66,000. And let me try to click here, but I don't think, let me see if there is a computation. You see that there is no computation, it's really strange. Anyway, no problem. They explain how to compute it, but not, there is not a formula. But anyway, it's no problem. So basically, as I said, you select the variable and you select the duration, and then let's suppose that you have an historical record, and then you compute on the historical variable, you compute this variable for the given duration. So let's suppose that your variable is average precipitation, again PT. And if you have an historical record, you're not required to compute the long-term average as we did before. You're required to compute the TDI, where I is a time index. So let's suppose that your variable is precipitation in August, and then you compute average precipitation in August. So basically you compute the average precipitation in August, so your D becomes August, and I refers to the years of the observation period. So you may have average precipitation in August for 1910, and etc. up to average precipitation in August for 2015. Good. And you get a sequence of values which you may consider this as a random variable. No problem. And therefore these are outcomes from this random variable, which is average precipitation in August. And these outcomes follow a given probability distribution, which in general is unknown, and it's variable. You know that if the average is computed over a long period, you know what is the probability distribution, because average over an increasing period are normally distributed. If it is a monthly average, it may be that it's quite close to normal. So given that drought are extended events, you are more likely to get the normal distribution with respect to floods, which is always an advantage. And in general, anyway, these are not normally distributed. So you should apply a transformation to make this data normally distributed. You know how to do it. Let me say, you know that it can be done, and you know one method for doing that, computing the logarithm. Okay? And given that usually these are positive values, you can take the logarithm. they are not always positive, because when speaking with droughts, the zeros may happen. So if you have zeros, then you need to do something, okay? Maybe that the logarithmic transformation is not the proper one. There are other transformations anyway. So you make them normal. Okay, and then you have your precipitation in August, for instance, in 2016. And then what you do is comparing the magnitude of precipitation in August in the given year with the probability distribution of these events. And what you do exactly is to compute. Let me indicate with the symbol sigma A or sigma PA. Let's do like that. The standard deviation of these variables. So let me also write a step here. Variable duration, time series, and here normal distribution, normal or Gaussian. Let me also write here, I forgot to tell you, with zero mean. Because if we make the data zero mean, it becomes simpler, the comparison. You know, when you transform the data to the normal distribution, as you know, it's very easy to bring them zero mean. Just compute the mean and subtract the mean from each value, and you get them zero mean. And then let me suppose that it has zero mean and standard deviation given by sigma the average A. Okay, we are here. Then let me compute this quantity P August 2016 average divided by sigma P August, and this is my SPI. And of course, you know, this has to be, this value has to be itself transformed to the normal distribution with zero mean by using the same transformation that you used to transform this data. So if the transformation is the logarithm, basically what I put here is the logarithm of, let me make it clear. And let me make it clear, sorry. Let me correct a little bit the indexes because I want to make it clear. So basically let me say sigma of the logarithm of PA, and let me indicate it here, sigma logarithm PA. Let's suppose that it's the logarithm, the transformation that we take. Sorry for making these corrections. So basically what I corrected is, these data are to be transformed, and let's identify them once transformed with the logarithm. Okay, let's suppose that the transformation is the logarithm, and then we get the standard deviation of the transformed variable, and then we compare the observation, the current observation, which is identified by the 2016 here. We compare its logarithm, we take the same transformation, we divide it by the standard deviation of the historical logarithms. And this is the SPI. This will be written in my web page. I will use another symbol for the transformation for indicating the normalized variable. In this case, I wanted to use the logarithm for the sake of clarity. And then, what do we obtain here? First of all, keep in mind that this is a zero mean variable. So basically, the logarithm, the transformation that we take, brings the variable to a zero mean. So if your observation, transformed observation, becomes negative, it means that you are below the mean. If it's positive, you are above the mean. So if you are usually above the mean, then it's not a drought, because a drought is defined as below average. So you have to be concerned by negative values of the SPI. And then you have suggested scales by the literature. So if your SPI, for instance, is below 2.1, below 2, it is a very severe, minus 2, it's a very severe drought. And you have a sequence of scales. I hope that Ernest defined the SPI in the same way, because there is ambiguity in the literature in how it is defined, and in particular there is ambiguity on whether this transformation should be computed on the variable or on the ratios, because this is a second possibility. You may compute the ratios by using the untransformed variables, and then you may transform the ratios. I prefer to transform them before. In my opinion, it's more rigorous. But still, you know, the literature is not clear. Okay, so this is the SPI, and as I said, for the indexes, I don't want to say more. I just want to say that there is an index called, I think it is called Water Surface Index, and there are different acronyms proposed by the literature, but it's the same index applied to the surface water. Let me see if there is something surface water index. Now it's surface water supply index in this case, so it's let me see. But as I said, there are different acronyms, so let's not focus on them. Indeed, this is a bit different. This is a bit different because it's also, it computes not only one variable, but more than one.
I think the abbreviation on Blackboard is different from what is searched on the internet.
Yeah, it's different, yeah. It's different. So in any case, I'm using a different acronym. But anyway, the message that I have for you is the same index as the SPI can be computed on other variables, and you will find on the web references. This one is that I Googled is a bit different, but that's I prefer not to go into the details. Now, The last thing that I wanted to speak with you is, this is drought forecasting, because these indexes allow us to estimate the intensity, what is called the intensity of a drought once it's occurring. But the relevant problem is, of course, that mitigation actions are not effective usually when the drought is already occurring. And then the next question is, can we predict droughts? And usually drought prediction is carried out by trying to predict relevant indexes. For instance, there are people who try to predict in advance the standardized precipitation index. There are people who try to predict in advance the indexes related to surface water availability, etc. And most of the efforts of researchers are concentrated in the prediction of meteorological droughts, because this is the real challenge, because the other droughts usually follow up. And usually droughts are triggered at the origin by a meteorological drought. So this is the big question. Can we predict meteorological droughts? You know that meteorological prediction made significant progresses in the past 20 years. And now for reduced lead times, we are able to perform very reliable predictions. But usually we know that meteorological predictions are reliable up to an horizon that is limited. And it is now extending. Now we are able to get a good prediction for 1 week of lead time, so 1 week in advance. But if we move beyond a couple of weeks, we know that the predictions are not reliable. I'm not sure if you paid attention. Sometimes the media say next summer will be very warm and very very dry. And usually when these predictions are issued, usually they are afterwards, they turn out to be not reliable, not true. And because it's really challenging. And meteorologists are basically trying a couple of two different kind of efforts. One effort is to try to extend meteorological predictions at the local level by using long-term meteorological models. And another effort is related to trying to predict global circulation patterns. So one thing is to use a meteorological model and try to extend the lead time, and one other thing is using climate models to try to predict global patterns. I think it is extremely interesting to discuss briefly what they are trying to do with the climate models, because in this area, indeed, we have some recent progresses. By using meteorological models, the progresses are still not very promising, but some interesting results were recently obtained by studying the global circulation patterns, and in particular, by studying the anomalies, the global scale anomalies of high pressure, which are usually identified with global scale phenomena like El Niño or La Niña. And I'm sure that you heard about them. And I want to dedicate some time with you to discuss on these two phenomena, what they are, and how the dynamics of El Niño and La Niña can be used to predict droughts. First of all, let's define them. So what is El Niño? And because even if these phenomena are quite known, indeed there is some misinformation on what they are. So let's focus first of all on El Niño. First, let me say that these phenomena are anomalous, global scale atmospheric circulations. So atmospheric circulation means the movement of air masses around the globe. And usually these movements follow patterns, seasonal and geographical patterns. And sometimes we experience some anomalies in this. And when there are anomalies in the global circulation of air masses, then they turn out in anomalies in the weather. And these anomalies usually are long-lasting. So if it is indeed true that there are these anomalies, and if it is true that there are connections with the weather, of course, this may imply that these anomalies cause droughts or extreme floods. Extremes, anyway, changes. Let me say changes. And changes means departure from average. Anomalous conditions means departure from averages. And therefore, indeed, this can induce droughts and floods, any particular droughts. And given that they are long-lasting, this may allow to make some predictions, like if we identify that we are experiencing now an El Niño event, and given that El Niño may last for a long time, we are able to make some predictions. And if we were able to predict El Niño with a couple of years in advance, that would allow us indeed to forecast droughts with useful lead time. So, let's see first of all what is El Niño. And let me say that El Niño is absolutely not related to climate change. El Niño is known since the Middle Age. There are witnesses of observations of El Niño hundreds of years ago. Of course, climate change may induce changes in the dynamics of El Niño. So it's a phenomenon that again, it's not new. So what happens? And let me refer to a map, because I need a global map to explain. See? Okay, yeah, I'm just trying to close it, because it's... Let me refer to a global map. You know, it's extremely easy if you Google El Niño. We get, first of all, a Wikipedia page, which, this is in Italian, sorry, but let me see if there is a map. I want a larger one, just 1 second. I will indicate to you a link that, in my opinion, is quite useful, which is obtained if one Google's cloud forecasting. But actually, let me see, I think it's this one. Yes, it's this one, which, you know, relates drought forecasting immediately to El Niño. And here there is another link that I will suggest you to the on NRO-AA page. Just 1 second, because here there is a map. Okay, this one refers to La Niña. The La Niña is the opposite of El Niño, so I can use the same map to explain. So basically what happens is that the temperature of the ocean, it refers to the Pacific Ocean. And what happens is that the temperature of the Pacific Ocean close to the United States, so the east of the Pacific Ocean, becomes warmer than usual. And therefore, here you have like a band of warm water, which is unusual. And there is, this is the definition of El Niño. So it's higher than usual surface water temperature in the Eastern Pacific. So close to the surface, you have what is called SST, which is surface sea temperature. It's higher than usual, close to United States and South America. And first, there is an important consequence for the aquatic life of the ocean, because there is displacement of cold water in the deep ocean. Normally, during, let's say, the autumn season, winter season, here you have some upwelling of deep water from the ocean to the surface. And the upwelling is favored by the fact that during winter, here you get cold water in the surface part of the ocean, so the deep water can upwell from the bottom to the surface. If the surface of the ocean keeps warm, you have displacement of deep water in the deep ocean, so you don't have this upwelling movement. And this is a problem for the cycle of the nutrients in the ocean, so it has an impact on the aquatic life. This is a first impact. A second impact is that if the ocean gets basically here warmer than usual, there is an effect, a direct connection with the higher pressure, which is not really explained. So this connection is not always, does not always occur, but there is a high correlation. So basically what we notice is that there is lower pressure in the east of the Pacific, high pressure I mean, with respect to the West Pacific. So basically, as I said, there is an implication which is not fully explained, but this warming of the ocean implies a decrease of the high pressure. And therefore, basically, you have here the high pressure that becomes lower than usual, and becoming lower becomes usually lower than the corresponding high pressure in the western of the Pacific. So what happens? What happens is that the winds follow, of course, the differences in high pressure. And usually, during the winter, it occurs that you have what are called trade winds, are the easterly winds. So we have, during the winter, in normal condition, atmospheric winds traveling from east to west, so in this direction. But if we get a lower pressure than average here, the winds tend to revert. And basically, if they revert, they change the circulation of the polar jet stream and the Pacific jet stream. So it changes the displacement of this jet stream, which are normally occurring. And what happens is that when we have La Niña condition, this Pacific jet stream is shifted northward. When we have El Niño, it's shifted south. So basically, this is important. Why? Because this jet stream bring wet and cool weather. And therefore, if it is shifted upstream, then we get basically dry here, because in normal condition this jet stream would travel south, and we get, so we don't get the wet weather here, we get the dry weather, and the wet weather is shifted upstream. And this is what happens. But this refers to La Nina. And with El Nino, you have the polar jet stream. Let me see, because I think there is a picture with El Nino. You see the difference in displacement. But this is today, but today it is, let me see if I will remember, okay, here. I think there is a nice picture here with both of them. Here. This is La Nina and this is El Nino. Let me see. This is El Nino. So if you remember the picture that we had before, the polar jet stream was more in the south, but what is important is to look at the wet part. The wet part is, let me show you the picture of La Nina. So now it's wet here, which is south of the United States. And you see that the same area gets dry. So during El Nino, you have basically, in fact, they say that the droughts in California are alleviated, are mitigated by El Nino, and are exacerbated by La Nina. And so basically, you see what is the effect. And also look at the different displacement of the polar jet stream. I go back and here. It's a different displacement. And this is what happens. So basically, and as I said, this direct connection between the surface sea temperature and these atmospheric circulation patterns usually happens very frequently, not always. So sometimes El Nino may occur without any implication on the circulation patterns. But there is a very good correspondence. So basically this is useful for prediction. The problem is that the El Nino and La Nina occur on average every 2 to 7 years. And we don't know how the next one will occur. This is the first problem. So basically the prediction 1 year or 2 years in advance is extremely complicated, and more than complicated, it's still not reliable. A second question is related to the duration of these events, because typically these events, the onset is in winter. So during the winter, if we look at the sea temperature, we may get an anticipation that something is occurring, but the problem is then that the duration of these events is extremely variable. So El Nino may last for up to a couple of years, but it may, a couple of years, let me say at most, and at least we observed also duration of just a few months. So even if we observe that the Nino is developing, we still don't know, because usually the way of observing it is measuring the sea surface temperature. But still we don't know if this will evolve in a difference, a shift in atmospheric pressure. And even if it occurs, we don't know what is the duration. So it's still extremely challenging to be able to say, okay, we are in May now, we see that El Nino is developing, then the summer and the autumn will be dry. This is extremely, and where? This is extremely challenging up to now. But, of course, this is a promising area, and a lot of research is moving forward. Okay, I think we can stop here, and then on May 25th, I will finish this topic quickly, and then I will speak about, to conclude my subject, on estimation of the human impact on hydrological processes. Human impact in general. Okay.